Okay, so I'm going to be going through the properties of logarithms, and you're going to want to have these handy for this week and next week. You're going to be using them for the next 2 weeks, basically. So writing them down, having a cheat sheet somewhere or somewhere in your notes so you can refer back to them, that would be really helpful. So I definitely recommend doing that. So before I get started on doing example problems, first I just want to go over what a logarithm is. And it is what we call the inverse of an exponential function. So when you have an equation and your variable is in the exponent, we call that an exponential function. And then the logarithm is what we call the inverse. Logarithms in general give you an idea of how big a number is. So an example here, base 10, which is, so when you have logarithms, you can have different bases, just like an exponent can have different bases, which is the number under the exponent. So a base 10 logarithm corresponds with something like 10 to some power. So you're looking at powers of 10. And so if you have a log of some number that gives you 5, and we use log as the abbreviation of logarithm, and then you have a second number that you take the log of and it gives you 3, if you subtract those you get 2, and that tells you, since these are powers of 10, it's 10 to the second power or 100 times larger, whatever number that you have. So it's giving you a sense of size, of how many powers of 10 it is. So if you take a logarithm of a number and it's between 2 and 3, the number is between 100 and 1,000. So logarithms in general just can give you an idea of how many powers of 10 it is. So something in millions, million has 6 zeros. So something in the millions, if you took the log of the number, would be 6 point something, basically. So taking a log just tells you kind of instantly, if you look at it, whether, oh, this number is in the millions or this is in the trillions, which sometimes is hard when you're looking at a number and you're looking at all those zeros. It's kind of hard to figure out how big this number is. And so looking at the logarithm, and it just gives you a single smaller number, and it makes it easier to deal with. So that's sort of like where logarithms started, is saying you've got some really big number. How do we make it smaller, something that we can understand? So that brings us to where logarithms are used. And any equation that you're involving size of something, sound intensity or earthquake magnitude, those use logarithms. Another one that I didn't list on here is light intensity. So when you hear about how strong a light is, like a star, how bright is the star, that number that they come up with, the equation to determine that actually uses logarithms. So if you're trying to figure out how big something is, usually logarithms are involved, just like how strong an earthquake is. Logarithms are also used when we're graphing things that are really, really big numbers, because you don't want to graph something that's in the millions. That would be really difficult to put in your graph. So instead, what people will do will take the log of the number, so that it's like a number usually between 1 and 10, and it's a lot easier to graph that's something really big. And so that will be described as being on a log scale, where we just took the log of the y values so that they're smaller numbers to graph. Now, the thing that happens here is it actually changes what the graph looks like. So you have to really understand what the logarithm is doing, because the shape of the graph changes when you use this trick. What happens is that things that are curved tend to become straight when you use this trick. Solving exponential equations, you use a logarithm to undo the exponent. So that's where you use its inverse property. So that way you can take something in the exponent out of the exponent so that you can start solving. And just in specific courses, logarithms pop up in pre-calculus, calculus, and then some engineering courses such as ET 310. So those who are going into more engineering specific fields are going to really need to remember these rules and properties, because they're going to come in handy later on. So if you know you're going down that route, you're going to want to make sure that you keep this stuff handy. So the mathematical definition of a logarithm is that, so for some number greater than 0, which is x, or some number, a, which is the base, greater than 0. So we always work with positive bases. And then as long as the base is not 1, you can rewrite a logarithm as an exponent. And so the logarithm is defined in terms of an exponential function. So you can change from something that's an exponent to something that is not an exponent. So where this comes in handy is if, let's say, somebody asked you what is, oops, let me make sure I made the pen. What is log base 2 of 16? And you're like, I don't know what that is. And you're trying to figure that out. You can take the log form and turn it into an exponent form to make it easier to understand. So when you convert it to an exponent form, what you're taking the log of is x, so that's going to be to the left 16 equals, and then the base is 2, and then you're basically saying 2 to what power gives me 16. So the log is basically giving you the exponent. So if you're trying to figure out the log of something, you're thinking about it as what exponent is this, and it depends on your base. So this is just saying for this particular problem, 2 to what power is 16, and your answer would be 4. So log base 2 of 16 is equal to 4, because 2 to the 4th power is 16. So the logarithm is hard to understand when you look at it in log form, but if you convert it to exponent form, it's usually it makes more sense. People understand exponents. So if you're going to graph a log, it's a function just like anything else. You can put f of x in front of it. And there is a button on most calculators that says log, and that's the button that you use. It does assume it's always going to be base 10. So if it's not base 10, you're going to have to use like the change of base theorem to do the calculation on your calculator, because the calculator only does 2 different types of logs. It does a base 10 or it does a natural log, because those are the most commonly used. And I do have a note here that graphing calculators are different because once you get into higher mathematics, the log is assumed to be the natural log instead of base 10, just because that's used more often. And so more like higher end, more calculators that can do higher end math, like a graphing calculator can do calculus, its log button usually is a natural log, not a base 10 log. So that's just kind of needing to understand that this symbol that we use for log is not always base 10. It depends on the context. But everything that we're doing in this class, if it just says log and there's nothing underneath it, then we assume that we're looking at powers of 10. So, but that's just a caveat, so that when you're, if you do any outside research, sometimes you might find something that's using a log and it doesn't mean 10. So you just want to be aware of that. So I mentioned the natural logarithm, and that's where your base is e, Euler's number, and e is about 2.718, I think. I know many digits of pi. Oh, I did have that right, yes. But e is one that you don't normally, it's not as famous as pi. But that is one of those numbers, and I think somebody might have talked about it in our constant discussion. But that's Euler's number, and so any logarithm that uses that as your base is called the natural logarithm, which we abbreviate ln. So this is the letters L and N, but in lowercase. So it's not 1n, it's the letters L, N. Usually I write it in cursive so that it looks like an L and it doesn't look like a 1, because then it can get confusing. Otherwise, if you want to write it in capital letters so you don't get confused, that's fine as well. But just make sure that those are letters, not numbers there. But the rules are the same for the natural logarithm. We just have a different symbol because we use it so often. And most scientific calculators have an ln button, and it's not confused with anything else. So if you see an ln button, that is the natural logarithm button. And you can hit that, use your calculator to figure out the number, the value. But what we're going to be doing today is not using our calculators. We are just going to be using the rules so that you understand the manipulation you can do with logarithms. And the reason why you need to know this is, especially if you're going on to calculus, is knowing these rules and knowing these properties can make your life easier when you have to do calculus later on. So that's why this is taught here, because it makes things easier down the road. And so you want to know the properties, and it's just a way to simplify things and another way to work with it. So going to examples here. Before I start going into all the properties, I just want to do some practice on converting between the different forms so that you get used to that. So these are all in log form, and we want to convert them to exponential form. So just as a reminder that our formula is, if we have y equals log base a of x, then instead we can write that as a to the y equals x. So the first thing to do is to identify the base. So I have log base 2 of 8 equals 3. So the base is 2. That's always what's underneath the log. So that's going to be under the exponent. And whatever your log is equal to is always the exponent. So this is going to be 2 to the third power. And then what the third thing you haven't used, I haven't used the 8 yet, so that's what it's equal to. So log base 2 of 8 equals 3 means 2 to the third power equals 8, which we know is true. Now, on the right here, I have log of 1,000 equals 3. So if there's no number written as an underneath the log, we assume it's base 10. So this is going to be a is equal to 10. So this is going to be 10, and then whatever it's equal to is always the exponent. So it's 10 to the third power is equal to 1,000. So what it's equal to becomes the exponent, and the number that's underneath the log is the base, and then the third number that's there is just what's kind of left over. So we can do logs even with fractions. So I've got log 9, base 9 of 1 over 81 equals -2. So our base is 9, and it's equal to -2. The log gives us our exponent, so that's -2 on the 9 as the exponent. And then that's equal to 1 over 81. Now, most of the time, logs and logarithms, natural logs, all those things don't come to whole numbers. So they usually come to decimals if you do it on a calculator, and usually it goes on forever. So this one on the right, I have the natural log of 7 equals 1.945. This is just rounded. The number goes on forever, but we can't write the whole thing, so we're just rounding it here. So if you see ln, that is telling you that your base is e. So I'm going to write e, and then my exponent here is 1.945, and then this is equal to 7. And it's not going to be exactly 7 because we rounded. So if you happened to do that on your calculator to verify, I get 6.99, which rounds up to 7. So the more digits you have, the closer we'll be to the actual value here, but we're just rounding. Are there any questions on converting from log form to exponential form? Yes. Phil?
How often are we going to, I mean, I guess, really deal with the LN?
It depends
Is that
on it, what degree. It depends on what degree you're going into. If you're going into an electrical or computer engineering degree, you're going to see it a lot. If you are not going into those, you're usually going to be dealing with just regular logs, not the LN. Does that answer your question?
it does? Thanks.
Okay. There are other questions. Okay. Now, because in college algebra, we have basically everybody takes college algebra, so that's why we have things that you may not have to know, like the natural log stuff. There are people who do need to know this, and so we cover it. Even if you may not see that particular version, you may just see the log version most of the time. So now this slide, we're going the other direction. We're going to take something in exponential form and practice writing it as a logarithm. So I'm going to rewrite a rule again, and I'm going to write it in the other direction here. A to the y equals x. That is the same as writing log base a of x equals y. So you're basically just identifying, you're looking at the pattern and you're identifying what a, y, and x are and then putting it into that little formula. So I have 4 to the third equals 64. So since 4 is under the exponent, that is the base. And then it's always equal to the exponent of 3. So that means 64 is what I'm taking the log of. So the log base 4 of 64 is equal to 3 is equivalent to writing 4 to the third equals 64. On the right, we have 10 to the fifth equals, looks like 100,000. I gotta count how many zeros I have there. This is one reason why we like logarithms. As you start getting those bigger numbers, it's kind of hard to figure out, well, how many zeros are there? So 10 is under the exponent, so this is log base 10. So then we don't usually write the 10 underneath it, we just write log. And so the log of 100,000 is equal to 5. Now on the bottom left, I've got 9 to the 3/2 power equals 27. So logs don't care if you have fractions or anything in your exponents. It's totally okay. So our base, what's underneath it, is 9. So this is log base 9 of 27. Your log's always equal to the exponent. So I know that's going to be equal to 3/2. And then we have e to the negative 3/4 equals, and again, this is an approximation. This is rounded because it would just go on forever. Usually you use 4 decimal points, so we've got 0.4723. If I write this as a log, it's going to be a natural log because it's an e, so that's going to be your ln. So I'm going to write it with a cursive, just that's my habit. And so I don't need to put the e. And so the natural log of 0.4723 is equal to negative 3/4. And again, this is an approximation when you have a decimal. And I have a button on my calculator to do that natural log. And it comes out to negative 0.750, and it has other decimals, but when you round it, that's negative 3/4. So we do end up having to round a lot of time when we're dealing with natural logs and stuff. So you're going to find this week you're going to be doing a lot of decimals. So a calculator is critical. Having a scientific calculator that can use these buttons, because you're going to be using decimals all the time. This is going to be like the one time that we generally don't deal too much with fractions. It's all decimal form. there any questions on these conversions? Okay. So now we're going to get into all of the properties. So the first one here is not really a property, but just a formula that I wanted to give you guys, and this is the change of base formula. And this is used if you're trying to find a logarithm of something that's not base 10 and not a natural log, which actually doesn't happen all that often. So you're going to get some practice with it on the homework on just being able to use this, but this usually doesn't come up too often, so you don't have to worry too much about it. Where this comes in handy is when we're solving exponential equations, and you usually do this by taking the log of both sides. This change of base formula says that if you don't want to take the log, you can also take the natural log of both sides. So when you're solving, this rule just allows us to use whatever button is handy on your calculator. Now, my scientific calculator has both a log button and a natural log button, but my graphing calculator has only a natural log button. So on my graphing calculator, if I'm using that, I usually just use the natural log instead of the log, which I'm allowed to do because of this change of base formula. But when you're solving and you have a scientific calculator, you have both buttons, it doesn't matter. Both of them work, which is kind of cool. So you can use whichever one is easier to get to when you're solving. And then solving stuff we're looking at more next week. So this is just here so you have the rule, but it's going to come in handy next week more. Now we have lots of properties of logarithms here. I've got the properties of logs and the properties of natural logs here. Those are on the top, and you can see that they're very similar. If you're taking a log or a natural log of 1, it's always equal to 0. And then it tells you why this is true, because anything to the 0 power is equal to 1. If you are taking a logarithm of a base and then the base matches what you're taking the log of, they cancel out and you're left with 1. And then we have the inverse properties and the one-to-one properties. And basically, the inverse property says that if you have a log of an exponent, those basically cancel out, or an exponent with a log. And the one-to-one property says if you have two logs that equal to each other, then the things inside the logs are equal to each other. So those last two are used for solving more than anything. And then the properties of logarithms, the first two, are also useful for solving. But those are good to know because those help you simplify things. Now, the other properties of logarithms that I have here underneath are the product property, the quotient property, and the power property. And these are what I'm going to be focusing on for the rest of my examples. And these actually come from our rules of exponents. So I'm actually going to make a note out of that. So these are derived from the rules of exponents. So if you remember your rules of exponents, if you multiply things together, the exponents add. And that's what we have right here with a logarithm. If you have a logarithm of things multiplied together, the logarithms add. Because a logarithm is basically giving you the exponent. So there's a connection there. We had a rule of exponent where if you're dividing things with exponents, you subtract the exponents there. And that's what we get the quotient property from. If you're taking a log of something divided, you subtract them because it's basically it's like you're subtracting the exponents. And then we have this power property, which is one of the most important things. And this one is used all the time. And that basically says that if you have a log of something with an exponent, you can pull that down in front and instead you multiply that log. So I'm going to zoom in here now that it doesn't let me take notes while I'm writing. So just so you can see that a little better here. So the power property says that the exponent on something you're taking the log of can just go in front of the log. And then we've got the product property and the quotient property, where if it's multiplied, you add them. If it's divided, you subtract. And these work for natural logs as well. If I can get it to slide. It does not want, there it goes. So the rules are the same for natural logs. And then there is this rule that there is no rule that allows you if you have things added inside a logarithm. There is no rule. You can't turn that, it doesn't distribute. So logarithms, the log symbol does not distribute. So you can't just take the log of u and the log of v. That is not allowed. So logs do not distribute. So you want to be very careful about that. So you can't separate those. So the next slides, I'm going to be using these properties, mainly the product property, the quotient property, and the power property. And I will make sure to label each step with each property that I used so you can see how we're using these rules. And these are everything on this slide. I would make sure that I write down somewhere, you have it somewhere in your notes, just so that when you're working with your logarithms, you can see what the rules are that you can simplify. And these are also, of course, in the textbook as well. So we're going to start with specifically rewriting these a certain way. So it says use the properties of logarithms to write the logarithm in terms of log base 3 of 5 and log base 3 of 7. So that's just telling us when it says in terms of, it means you need to use these things in when you rewrite it. So you can't have the log base 3 of 5 over 7 like we have. We need to only use log base 3 of 5, log base 3 of 7. So we have log base 3 of 5 over 7 here. So we've got a fraction here. We're taking the log of something that's divided. So this is the quotient property where you subtract them. So instead, we can write this as log base 3 of 5, which is the top, minus the bottom, log base 3 of 7. And this is the quotient property that allows us to do this. So you're taking something that had a fraction in the log and you're separating it out. And now we're filling the directions because it says to write the logarithm in terms of these things. And so we have a log base 3 of 5, we have a log base 3 of 7, so we're okay. And then you can't simplify any further. You would have to then go to a calculator or use the change of base formula to actually figure out what this is. But we're just rewriting it. We're not really simplifying, we're just practicing our rules. Now, the second one here is going to be actually more than one step because we have the log base 3 of 35. So right now, we can't do anything with it as it is, but we can separate 35 as two numbers multiplied together so that we can use the product property. So log base 3, instead of writing 35, 35 is 5 times 7. So I can write that as log base 3 of 5 times 7. Now I have a logarithm of things multiplied, and this is where we use the product property where we can turn this into addition. So this is log base 3 of 5 plus log base 3 of 7. And this is the product property. And now we've rewritten this in terms of log base 3 of 5 and log base 3 of 7. So all we're doing is just practicing using the rules, writing this in different ways, because when you go on to calculus, for those of you who have to, this is going to be very handy. It's going to make things easier for you. So what we did here is often called expanding. because you're taking something that's simple or small and you're making it bigger. So it's often called expanding the logarithm. So you're making it larger, basically. Are there any questions on these two examples? As a side note, as I'm thinking about it, in Alex, there should be a button that will look something like this when you're doing these types of problems. So when you click that, you want to make sure that the first box is where you put the base, where you would put like 3, and then the second box is where you'd put the other thing, the 5. And you have to use your cursor, your arrow keys to kind of get out of one box and into the other box. So you have to just pay attention to the size of your cursor, that vertical line that flashes and moves, so you have an idea of where you're at. But that's the button that you would use. And if you are someone who likes to type your stuff in, you would type this in as log underscore, and then you would put in your base. So let's pick base 3, and then you would have a space, and then you would put 5, and that should give you the same thing. So if you're trying to ever get something underneath something, that's an underscore button. And that will put it in the right form, so when you're trying to type your math out. Okay, so here we're going to use our properties and rules to find the exact value of the logarithmic expression without using a calculator. So not everything can be done without using a calculator. Most of them can't, but these are designed so that you can use them without a calculator, just so you can practice using the rules. So I'm going to start with log base 5 of 1 over 125. So you want to kind of think about this as a puzzle. Some people describe math problems as a puzzle. You're trying to figure out, how do I do this? How can I rewrite this to make it easy for me? So our base on the log is 5. So we want to rewrite 1 over 125 so that it also has a base of 5. We want to turn it into something with an exponent so that we can cancel things out. So I'm going to start with 125. So 125 is actually equal to 5 cubed. And you can do a prime factorization there to figure out what it's equal to. So I'm going to rewrite this as log base 5 of 1 over 5 cubed. Now I'm going to use my rules of exponents, and instead of writing 1 over 5 cubed, I'm going to write it with a negative exponent. So when you do that, you basically take the reciprocal and then the exponent changes sign. So this becomes 5 to the negative 3. So now I have log base 5 of 5 to the negative 3. And this is one of our rules of exponents, where if your base on the log, or rules of exponents, rules of logarithms, one of the properties of logarithm says if your base on the logarithm matches your base of what you're taking the log of, those can cancel out. But right now we can't cancel it out because we have this negative 3 in the exponent. So we have to use our other rule where that negative 3 can be put in front. So that is, I always forget the name of this rule for whatever reason. What is that, what they call the power? Yeah, the power property. So we're going to use the power property here. So I can put that negative 3 in front, and that's basically multiplied by the log base 5 of 5. And so I used the power property in order to do that. The exponent could go down in front. Now, the log base 5 of 5, those cancel out and you're left with 1. So we usually, this is a way that we use in math to kind of indicate that, is we kind of like cross it out and then we'll do an arrow to what that's equal to. And so this would be equal to -3 times 1, or just -3. And so that ability to cancel out the log base 5 of 5, if I go back to my properties, that is the property number 2. It doesn't have a name, but it's where oh, I shouldn't have used yellow. That's not helpful. This one right here, it doesn't really have a name. But if the base is the same as what you're taking the log of, those cancel out and those become 1. So we use that. It doesn't have a name, so I don't really have anything to write down for that one. But that allows us to simplify, and so we get an answer of -3. Now the one on the right, I have a natural log, so that means it's base e. And I have 1 over the square root of e. So I'm going to do the same sort of trick here. First, instead of writing the square root of e, we're going to write it with its exponent version. We don't use this very often, but the square root is the same as the 1/2 power. So I don't know if you remember that earlier when we were talking about radicals, but those are the same thing. So we're going to rewrite it as an exponent instead of a square root, because then that will allow us to simplify here. So now I'm going to do the same thing I did before, where I'm going to take the reciprocal, which changes the sign on the exponent, which gives me e to the -1/2. And then I'm going to use that same power property that I used in the first one here to put that exponent down in front. So we'll get -1/2 times the natural log of e. And that is, again, using the power property. And then this is, again, it is rule number 2 that doesn't officially have a name, where your natural log has a base of e. So the natural log of e is equal to 1. And so that just disappears, which leaves you with an answer of -1/2. So we're doing a lot of manipulations here in order to simplify. And this is why these rules exist, so that you can take something that looks complicated and rewrite it another way. And it's all about thinking, well, how else do I know to write this? Let me try that and see what I can do with it. So you really start working with all the rules that we've seen earlier, with the exponents and square roots, and you're just using them in different ways, writing them differently in order to simplify. And this is a skill that is used a lot in calculus. Are there any questions? Okay, so now we're going to do things without just numbers. We're going to have variables and all this stuff. Oh, how did the e get canceled in the second one? So that is going back to rule number 2 here. And the natural log of e is equal to 1, because the natural log is the same as the log base e. So the log, let's write this. Log base e of e is equal to 1, because those cancel out, and that goes back to the rule 2 under basically the same rule for both of these. It's number 2. where those are equal to 1. And that's because if you wrote it in exponent form, e to the first power equals e. And so the log tells you what power do I need to get e from e, and that's just a power of 1, just an exponent of 1. So you're going to want to, when you're working with stuff this week and next week, you're just going to want to memorize that because you're going to be doing it all the time. All the time. So when you go do enough practice problems, you will have it memorized. Are there other questions? Okay. So here I've got logs, I've got variables and numbers, and so we're just going to practice using the properties to expand. And so basically what that means is if you have anything multiplied together, you're going to turn that into adding logs. If you have anything divided, you're going to turn it into subtracting logs. And then if you need to rewrite exponents as needed, you also use the power property to put those exponents down in front. So I'm going to start with the left here. We have a log base 4 of 11b squared c. So these are all multiplied together. So the first thing that we do is turn this into addition of logarithms. And that's using the product property. So this is log base 4 of 11. Then you go to the next letter and you separate each letter. So the next one would be b. So that would be log base 4 b squared. Then plus log base 4 of c. So that is using the product property. The next step is we need to take any exponents and put them down in front. And that's using the power property. So there's only one thing that has an exponent, so that's the only thing that's going to be changed. So we have log base 4 of 11 plus 2 times log base 4 of b plus log base 4 of c. And that's your last step. So once you've done that, you have expanded it out. You can see how it got bigger. So what we did here is our first step, we used the product property. And then we used the power property. And we took something very small and we made it bigger. We're going to do the same thing on the right. And on the right, we have a natural log. And in this case, once you have a square root, you can't start using any of those rules, or we have a cubed root in this case. We can't use any of those rules until we turn that into an exponent. So that's actually going to be the first thing that we're going to do, is we're going to rewrite the cubed root as an exponent. So I have the natural log, and then I have yz over x squared, and then a cubed root is equal to the 1/3 power. So I'm just taking the entire cubed root and rewriting it as an exponent. Now, when you have an exponent here, we can't use our quotient rule until we move the exponent, because it's inside parentheses here. We have this exponent on it. So we're actually going to do things in a different order than we did on the first one here. So we're going to take the exponent, we're going to put that down in front first. So we're going to use the power property. So we can get that out of the way so that we can start expanding the rest of it out. So that's going to give us 1/3 times the natural log of yz over x squared. Once you get rid of that exponent, now we can use the quotient property where you have the natural log of the top minus the natural log of the bottom. You can separate that out. So we're going to use the quotient property. So I still have my 1/3, but we have to be careful here because that 1/3 is multiplied by the natural log part. So everything that follows is part of that multiplication. So I'm putting it in parentheses. So we have the natural log of the top, which is y times z, minus the natural log of the bottom, which is x squared. Now we're going to do two things because I'm running out of room here. So I'm going to combine steps. I should have made this a slide by itself. We're going to use the power property again so that we can put that exponent of 2 in front. And then we're going to use the product property on the yz so that we can separate that into addition. So we're going to have our 1/3 and then parentheses. And then the y times z becomes the natural log of y plus the natural log of z. That's our product property where that becomes addition. Then I'm going to have my minus 2 natural log of x because I used the power property. And then our final step of expanding is to multiply that 1/3 through the parentheses. And that's what will be considered expanded out. So we get 1/3 times the natural log of y plus 1/3 times the natural log of z minus, and then 1/3 times 2 is 2/3. So that's going to be 2/3 times the natural log of x. And the reason why we practice this is for those going into pre-calculus and going on to calculus is you put things, you expand them out so that you can do an integral or derivative, which are calculus things that you do. And then what you do is after you do that, you condense it back together. But they're usually easier to do these operations of integrals and derivatives when they're expanded out because they're simpler. You have chunks, smaller chunks to work with rather than a big giant thing. So this is like an intermediate step that has done a lot of calculus, which is why we're practicing it now. Any questions? Okay, so these are my last two. And now we're going to go backwards. These are already expanded out, and we're going to use the same properties to condense them together. This is a really good way to make sure you know those rules. It kind of tests you. Can you go back and forth between? Can you undo what you did? So I'm going to start with the one on the left. We have 2 times log base 2 of x plus 4 times log base 2 of y. So I'm using all of these properties in reverse. So instead of going from, I go back to my properties list. Instead of going from the left side to the right side, I now have something in the right side form and I'm going to the left side. So we're just switching the direction that we're going with these properties. So the first thing that we do is if we have any numbers in front, we put them back into the exponent. So we're using the power property. Help if I actually spelled that right. So that's the first thing you do, is anything that needs to be an exponent or was an exponent gets put back up there. So this will give us log base 2 of x squared plus log base 2 of y to the 4th. Because the first part had 2 in front, the second part has a 4 in front. So now those become the exponents. So we just use the power property in reverse. Then we're going to reverse the product property, because we have things that are added and we undo that and we turn them into things that are multiplied. So that is the product property. And we're allowed to do this as long as they're the same base. So there's both log base 2. So now we turn them into a single log multiplied together. So the log base 2 of x squared y to the 4th. And once you've put it all together in one single thing like that, that's your condensed version. So we're really turning your brain around and getting you to think about these in another way, which is really good skill, is try to undo something that really gets you know, you're so used to going one way, and when you have to undo it, it's like it works your brain, but it's really good skill. So I'm going to do the same thing on the second one here. I have 2 times the natural log of 8 minus 5 times the natural log of z minus 4. So any numbers in front of the natural logs, I'm going to be using that power property to put them back up into the exponent. So those are going to be moved back up. And so we get the natural log of 8 squared minus the natural log of z minus 4 to the 5th power. Now we want to condense this, so 8 squared, we can actually just do 8 squared and rewrite this as the natural log of 64. So I'm just squaring the 8 just so that I can, because I'm trying to make this as small as possible, and so that means if you can get rid of an exponent there and a number, go ahead and do so. So now we have things that are subtracted, and that's telling us that we need to undo it with the quotient property. The quotient property says if they're divided, they become subtraction. So here we're subtracting, so it becomes division. The first thing is going to be on the top, the second thing is going to be on the bottom. So these are going to be under the single natural log, and so 64 is going to be on the top, and then z minus 4 to the 5th is on the bottom. And once you have that single thing in the log or the natural log, that's when you're done and you have condensed it out. Are there any questions? While you guys think of questions, I think I'm actually going to open up Alex just to give you, just kind of show you in Alex how these questions show up. Yeah, Phil, go ahead.
I was just wondering, hey, I know we did the subtraction. I'm thinking about where we have the ln 64 minus ln z minus 4 to the 5th.
Mm-hmm.
And I'm used to, I guess we normally have a negative, like a -5, and that would normally tell me that
yes, because that tells you that it's on the bottom. But
Right.
that's where the subtraction is coming from, is that negative, because the natural log or the logarithm is in the exponent, or it's telling you instead of the actual exponents having the negative, the natural log has the negative. So that's where the subtraction comes from with the natural log. So that's sort of equivalent to the -5. It's hard to get used to, because yeah, you're like, oh, I have this exponent, I should have had a negative exponent, but the natural log is like it's a new, it's I don't know what the right word is. It's like a new thing you can do, like adding. You learn how to add. It's an operation. Like the natural log and the logarithm's new operation, and it's like, this is how it works. We don't have negative exponents when we have these, or we don't have to follow that same rule, because it's something else. So yeah, I mean, it's kind of, I hope as you practice it, it will start making sense. And it's good that you're thinking, oh, well, this should be negative, because that's like your rules with exponents, and that's good, because that means you have those rules of exponents. But this is like a total different operation, so it doesn't work the same way.
Okay, so we have to really be mindful of the operation, the sign there.
Yes. Yeah. You have to really think about, what am I doing? If I'm dealing with logs, then I don't need that negative in the exponent thing. So yeah, you have to really pay attention to like what you're doing and all that. So I have the optional assignment on properties for logarithms up just so you can see. So this is, I don't want to bring up the actual assignment. So for some of these, they actually give you the boxes, and so you enter into each box what you need to do. If you need a fraction, then you can put a fraction, but you may not need it. For the ones where you're expanding, this is a log 10, so they only give you the option with the log. So you don't have to worry about putting in the base 10, because they give you the one that you need here. So you just need to hit the log. Now notice it has 2 boxes here, but when I clicked log, only 1 box showed up. So if I need to put a number in front of the log, I have to hit my arrow key to the left so I can type that. And then I go to the right, and then I'm back in the box. So usually what I would do here is, let me clear, is I would do any numbers in front first. So like that 7 on the exponent would be in front. Then I would log button. And this is log y. And then I would hit my plus. So you want to make sure, I don't know why it's showing up funny, like it looks like it's in the log. But you want to make sure that like after you type it, you're out. So I want to hit a space bar, make sure my arrow's to the right just to make sure I'm outside of it. Then I'm going to do my plus. So if your plus ends up really next to the y, that means you're still inside the log. So because I got a space between my y and the plus, I know I'm outside of the log. And then I can hit my button again and then type in my z. So I'm going to just check. So you want to be very careful about the spacing, because if things are right next to each other and there's no space, that means you're still inside the log. That's usually where people are having errors with Alex. They start putting things in the log when they don't need to be in the log. So this would be another one, like I'm going to have a 1/3, and then I'm still in that fraction where the cursor is. So I have to hit my arrow to the right to get out of it, and then I want to hit my log button. And then if you want to make sure everything you type is in the log, parentheses are a good way to do that. So, and if I close the parentheses, then I can make sure that I'm outside of the log. So if you want to make sure you're not making any mistakes, even if it's just a log of x, you can put parentheses in there just to make sure that you have what you want inside the log, just to be safe. And here's an example where these have a different base, but they have kind of put that in there for you because it's a write-in expression as a single log. So they've kind of put in the spot where you put in the base b, and then you would put whatever you're simplifying there. So they've kind of set that one up for you. Oh, oops. I'm going to save that whole thing for later. Go back to week 7. All I wanted was to go to question 9. So, and then here, it's just a practice of the change of base formula. So you have to make sure that you're rounding where you're just putting in a number. I don't think there's going to be anything in Alex that's too hard, just as long as you're mindful of where your cursor is. So are there any other questions that you guys have? Okay, well, I'm going to assume that you guys don't have any more, but hopefully this is helpful. I know logarithms are really, the properties part really throws people for a loop. Teresa, yeah, go ahead.
Oh, I didn't have a question.
Oh, it looks like you unmuted yourself, so I thought you had a question.
No,
yeah.
I understand it while you were going over the examples.
Good. So the key is look at other examples in the textbook, make sure you have those rules written down so you know what rules to look at, and doing the practice problems, those optional problems. There's not too many of them for this week, for this particular topic, but that can help you get some extra practice as well. So, all right. I appreciate that you guys have joined me on a